In our last segment, we studied a classic problem in magnetostatics, and the problem was the magnetic field above the center of a current carrying loop of radius r. Now, the expression that we obtained from the magnetic field at this point on axis was the following. It becomes useful when we look at a solution of this kind to consider it in different limits. We could consider it in the limit where the point of observation is very close to the center of the loop. That is where we're down in, let's say, in this region here, where the distance from the origin is small compared to the radius, or in the limit where the distance from the origin becomes very large compared to the radius. Alright, so this is a very common calculation in physics because it often gives us simpler forms for the equations, and often we are in one of those two limits. We don't have to be, but often we are. So if we took the limit that z was, let's say z was extremely large, we're going to come out here and we're going to take z to infinity, the lowest order term can be obtained simply by neglecting r in the denominator. Very straightforward. And similarly, if we're very close to the center of the circle where z goes to 0, we can disregard z, but it becomes a little more interesting if we'd like the lowest order correction to those results, and that's what we're going to do here. Okay, so this expression that you see here is the same expression that I wrote on the previous page, but I factored z squared outside of the term downstairs to create a z cubed. But more importantly, I now have a dimensionless parameter, r divided by z. This has no dimensions, and it is a parameter in the limit that we're considering, which is small compared to 1. And so now I can expand this term here. I can expand this term here in the denominator. So let's have a look at that. If I have an expression 1 plus a small quantity raised to the power n, where epsilon is much, much less than 1, and where n is integer, non-integer, positive or negative, the first order term in the expansion is 1 plus n epsilon. This is the lowest order term, and it's a very, very useful result. So let's apply that result to our present equation. The small term that we have then is this one. R is divided r on z squared, and our n is 3/2, or perhaps we should write it as minus 3/2. So we're going to expand that quantity in the following way. Okay, so there is our new expression for the magnetic field in the large z limit, large z meaning z very large compared to r, and we not only have the 0th order term that we discussed earlier, but we also have the lowest order correction. It's actually second order in our small parameter, and that's a rather interesting result. So if we were to work in the small z limit, where it was in fact z on r, which is the small parameter, all we would do would be to interchange z and r here, and of course z and r here. So this would become r cubed, and this would become z divided by r squared. So let's write down those two results in those two limits, and then have a look at we'll have a look at some symmetries and see what we can learn. Okay, so there are our two equations in these two quite different limits. If we were to look at, let's concentrate on the lower equation. This is valid near the center of the circle. The zeroth order result at the circle is just this term, and the first correction is this term. Now, if we look at this, you'll notice that this solution near the center of the circle is even in Z. Right, so it doesn't matter whether Z is positive, we're looking above the circle, or negative below the circle. It's telling us that the magnetic field in this approximation is the same. And it's interesting to ask the question, would we expect that result? And indeed we would. If you think about it, the symmetry of the problem tells us that that must be the case. It tells us straight away that we could never have a linear correction term near the center of the circle, nor could we have a cubic term, nor any term which is odd, an odd power of the small parameter Z divided by R. So looking at different asymptotic results and considering symmetry can give us insight into a solution. It can also be a useful check on whether we think the solution is correct. Had we done this and found that we had odd terms in our expansion, we'd know straight away from symmetry that the result was wrong.
Well, let's apply that reasoning then to the first equation that we have here, the equation which is valid in the large Z limit. Let's check the symmetry and make sure that it does indeed make sense. You'll notice that the correction term here has the correct symmetry. It is even in Z. So bear in mind this is not valid as Z goes to 0. So we have no issue with this solution blowing up at Z equals 0. It's simply not valid there. We've constructed it for large Z, and in that limit this term is even. However, the zeroth order term has a problem. The zeroth order term is Z cubed. Now, although the dependence may be correct, that is, the dependence on Z may be correct, the symmetry clearly has an issue. It cannot be right. If you go back and have a look at how we obtained this Z cubed term, inside the parentheses was a Z squared term. We took its square root and then we cubed it. And there we made a small error. So let's fix that up at this stage and ensure that our symmetry is indeed correct, and we'll do that by integrating that this must be the modulus of this quantity. That is, it is the positive term